A grain of pollen of mass m starts at rest and falls through the air on a day with no wind. Determine the position, velocity, and acceleration as functions of time. Let's draw a three-body diagram. The dot represents the grain of pollen. Force of gravity, Fg, is down. Drag force, Fd, is up. Acceleration is down. And the x-axis is positive going downwards. And let's start it at x equals 0. Let's write the differential equation. We'll apply Newton's second law to this free-body diagram. We'll take down to be positive. So the net force is Fg minus Fd. Since the force, drag force is upwards, I put a negative sign in front of it. And that equals mass times acceleration. Now, the force of gravity is equal to mg. The drag force is equal to bv. This is pollen. It's very small, so it's going to be a viscous drag. And then the acceleration is dv by dt. So let's put these three things into our equation for Newton's second law, and this is what we get. This is our differential equation. mg minus bv equals m dv by dt. Now we need to solve this equation for v. How can we solve it? Yes, Isabel is correct. We solve it by separation of variables. Good answer. So here's our equation. And what we want to do is put all the v's on one side and all the t's on the other side. So here, we divide by mg minus bv, and we multiply by dt, and this is what we get. Now, the left side has the v's, the right side has the t's. So these variables are separated. Now we can integrate. This is what we get. I took the m outside of the integral, since it is a constant. To solve this integral, the integral on the right is easy. It's just t. The integral on the left is a little bit more difficult. What we can do is a u substitution. Let's say u equals mg minus bv. Then we'll take the du. Since mg is a constant, du equals negative b dv. So let's solve this thing for dv. And we get this. dv is negative du over b. So now what we want to do is replace dv with negative dv over b. So make that replacement there. And instead of mg minus bv, we'll put u into our equation. So make those two replacements. And this is what we get. Negative m over b du by u equals dt. Now let's multiply through by negative b over m, and this is what we get. So now it's easy to solve this integral. Du over u is ln u. Integral of dt is t. So this is what we get. ln u equals negative b over mt plus c1, where c1 is a constant. So this is what we have. Now, we don't want ln u, we want u. So let's take e to both sides of the equation. So e to the ln u equals e to negative b over mt plus c1. This exponential function on the right can be written as two factors, like this. E to the c1 times e to negative b over mt. E to the c1 is just another constant, which I can call c2. And e to the ln u is just u. So this is what we get. U equals c2 e to negative b over mt, where c2 is a constant. Now let's put what u is. U is mg minus bv. So we get mg minus bv equals c2 times e to negative b over mt. Now we need to find that constant c2. So we need to determine it. How do we determine it? Yes, Yes, Giselle is correct. We need to find some initial condition. What do we know? What was the velocity at the initial when t equals 0? The object started at rest. So we know that at t equals 0, v equals 0. This is our initial condition. Let's put these two things into this equation. This is what we get. mg minus b times 0 equals c2 e to negative b over m times 0. Well, this term is 0. This is e to the 0, which is 1. So we get mg equals c2. Now put the mg into our equation for c2, and then this is what we get. mg minus bv equals mg times e to negative b over mt. Now we need to solve this equation for v. So we can rearrange it like this. Then we could divide by v and then take out a common factor of mg over b. And this is what we get. Here's our solution. v equals mg over b times 1 minus e to negative b over mt. Let's see if this solution makes sense. Let's check it. So when t equals 0, or what does this solution give us? When t equals 0, this exponential function is e to the 0, which is 1. So we have 1 minus 1, which is 0. So when t equals 0, v equals 0. That's what we expected. We started at rest. Now let's look at when t goes to infinity. When t goes to infinity, the exponential function becomes e to the negative infinity, which is 0. So this is 1 minus 0. And so v is mg over b. That is a constant. It doesn't depend on time. And after a long time, we expect v to become a constant equal to the terminal velocity. So our equation makes sense. Here's what we got for the v. Now we want to find the acceleration. Well, acceleration is dv by dt. So we just have to differentiate this function. Let's do that. Take out the common factor mg over b right here. Derivative of 1 is 0. And then we have the negative. And then we differentiate e to negative b over mt. To do that, we could use the chain rule. Differentiate with respect to negative b over mt. That gives us this. E to negative b over mt. And then differentiate negative b over mt with respect to t, which gives us negative b over m. So now things here cancel out. We have the v cancels out over here. M cancels out. And we're left with just g. And so our solution becomes a equals g times e to negative b over mt. Let's check this solution. When t equals 0, this exponential function becomes e to the 0, which is 1. So a equals g. When t equals 0, the drag force is 0. The net force is mg, so ma equals mg, acceleration equals g. When t goes to infinity, this exponential function becomes e to the negative infinity, which is 0. So therefore a equals 0. And after a long time, we reach terminal velocity. Velocity is constant, so the acceleration must be 0. So our solution makes sense. Now let's calculate the position. v equals dx by dt, and it also equals this. mg over b times 1 minus e to negative b over mt. That's what we just calculated for the velocity. So we need to solve this differential equation, and again, we can use separation of variables. Multiply both sides by dt. This is what we get. So now we have x on the left side, t's on the right side, and we can integrate. this is what we get. So let's do that integration. So integral of dx is just x. Then integrate of this first factor, 1 is just t. So mg over b times t. Then we have the constant negative mg over b, so negative mg over b, times negative m over b, times e to negative b over mt plus c. C is a constant. The result of an integral, if we differentiate the result of an integral, we must get what's inside the integral. So if we differentiate this, we must get this. If that is true, then this is the solution of the integral. Let's look at this. d e to negative b over mt by dt is negative b over m times e to negative b over mt. So each time we differentiate this exponential function, we get a factor of negative b over m coming in front. So we don't want this negative b over m in front, because we want just this. So that's why we multiplied by negative m over b. If we multiply by negative m over b, then the m's are going to cancel out, and the b's cancel out, and negative times a negative is positive, and so we get e to negative b over mt. So that's just a verification that this is the solution of this integral. Let's simplify it some more, and this is what we get. mg over b times t plus m squared g over b squared e to negative b over mt plus c. Now we need to find that constant c. What is the initial condition that we can use? What was the position when t equals 0? Correct, Isabel, good. When t equals 0, x equals 0. So let's put t equals 0 and x equals 0 into our equation here. And this is what we get. 0 equals mg over b times 0 plus m squared g over b squared e to the negative b over m0 plus c. Well, this term is 0. This exponential function is e to the 0, which is 1. And so c is negative m squared g over b squared. Now, put the c, this c, back into our equation, and we get our final answer. X equals negative m squared g over b squared plus mg over bt plus m squared g over b squared e to negative b over mt. That looks like a pretty complicated function. To understand this function, let's see what it is when t is close to 0 and when t is very large. So when we want to get the position near t equals 0, what we should do is doing a Taylor expansion of this exponential function, e to negative b over mt, about t equals 0. So this was Taylor's formula, up to second order in t. F at t equals f at 0, plus t minus 0 f prime at 0, plus t minus 0 squared over 2 factorial f double prime at 0. F at t is this. When t equals 0, it is just 1, because e to the 0 is 1. F prime at t. When we differentiate this, we're going to get a factor of negative b over m coming in front. So we get negative b over m, e times e to the negative b over m times t. At t equals 0, this becomes e to the 0, which is 1, so we get negative b over m. Second derivative. When we differentiate again, we get another factor of negative b over m coming in front. So we have b squared over m squared times e to the negative b over mt. When t equals 0, this becomes e to the 0, which is 1. So f double prime at 0 is b squared over m squared. So now, let's put these things into our expression. So 1 goes here. Negative b over m goes here. And b squared over m squared goes here. And this is what we get. E to the negative b over mt is 1 minus b over mt plus b squared over 2m squared times t squared. So let's use this expansion near t equals 0 in our result for x. So there's our expansion. This is x. So now we're going to replace e to the negative b over mt in red with this expansion. Make that replacement. And this is what we get. Now certain things are going to cancel out here. This term and the 1, negative m squared g over b squared plus m squared g over v squared, that they sum to 0. So that cancels out. Also, this term, mg over b times t, is going to cancel out with this term, b over m, because m squared g over b squared times b over m is mg over b. So they cancel out. So this and this cancel out. And what are we left with? We're left with the final term. And look, the m squared cancels with this m squared. The v squared cancels with this v squared. And what we are left with? We are left with g over 2 times t squared. So this is what we get. Near t equals 0. X equals 1/2 gt squared. This is same as position when there is no drag force. So when t equals 0, velocity is 0 and there's no drag force. So the acceleration is g, the acceleration due to gravity. And using the kinematic equations, the position would be 1/2 gt squared. So this is what we expect it to be. That's good. Now, let's look at the position at large times. At large times, when t becomes much larger than m over b, this exponential function becomes 0. And then, so then we get rid of this term goes away. And this is what we're left with. X equals negative m squared g over b squared plus mg over b times t. This is a linear function. The position is linear at large times. If we have a linear position function, then we will have a constant velocity, and that's what we expect it to be. At large times, we have a constant velocity. So this thing makes a lot of sense. The slope of the linear position function is what's in front of the t, mg over b. And this slope is the terminal velocity. So the terminal velocity is mg over b. The time constant. This is the acceleration, ge to negative b over mt. We can write that acceleration as ge to negative t over tau, where tau is called the time constant, and tau equals m over b. The time constant is measured in seconds. It has to be in seconds because the argument of the exponential function must be dimensionless. So t is in seconds, the tau must also be in seconds. Another way to see that, mass is in kilograms, b is in newtons per meters per second. And if you work that out, you'll find that it is in seconds. Let's see how acceleration changes when we increase the time by the time constant. When t equals 0, a equals g, because e to the 0 is 1. When t equals tau, a equals g times e to negative tau over tau. This is e to negative 1, which is 1 over e. So a equals g over e. When t equals 2 tau, a equals g times e to negative 2 tau over tau. This is e to negative 2, which is 1 over e squared. So we get g over e squared. Note, when we go from t equals 0 to tau, we've decreased the acceleration by the factor 1 over e. When we go from tau to 2 tau, we decrease the acceleration by the factor of 1 over e again. When the time is increased by tau, the acceleration is decreased by 1 over e. Let's plot the acceleration versus time. This is the equation that we are plotting. Acceleration on the vertical axis is written in terms of g. The time on the horizontal axis is written in terms of tau, the time constant. Here's what we get. It starts at g at t equals 0, and then it exponentially decreases to 0. And it's pretty much close to 0 after a time of 5 tau. So after a time of 5 tau, we can say that the system has reached steady state. Look at this factor e to the negative t over tau. When t equals 0, it is 1. As t increases, it gets closer and closer to 0. When t equals 0, the acceleration is g. It is g away from the final value of a equals 0. When t equals tau, the acceleration is g over e. It is now g over e away from the final value of 0. When t equals 2 tau, the acceleration is g over e squared. It is now g over e squared away from the final value of a equals 0. When the time increases by tau, the acceleration gets closer to 0 by a factor of 1 over e. Velocity and time constant. This is the velocity. Using the time constant, we can write it like this. Vt times 1 minus e to the negative t over tau, where Vt is the terminal velocity. Tau is m over b, Vt is mg over b. Let's see how the velocity changes when we change the time by the time constant. When t equals 0, v equals 0. T equals 0, this is e to the 0, which is 1, so 1 minus 1 is 0. When t equals tau, v is vt times 1 minus e negative tau over tau. This is e to negative 1, which is 1 over e, so it becomes vt minus vt over e. Note, at t equals tau, it is vt over e away from the terminal velocity. When t equals 2 tau, v is vt times 1 minus e to negative 2 tau over tau. This is e to negative 2, or 1 over e squared. So it becomes vt minus vt over e squared. Note, at a time of 2 tau, it is vt over e squared away from the final velocity of vt. When the time is increased by tau, the velocity gets closer to vt by a factor of 1 over e. Let's look at the graph of velocity versus time. Here we are plotting this function. Vertical axis is in terms of vt, horizontal axis in terms of the time constant tau. Here's what we get. It starts at 0, and it increases. As it increases, the slope of the tangent line becomes smaller and smaller. That means the acceleration is becoming smaller. Eventually, the slope becomes equal to 0 over here, and it moves at constant velocity, the terminal velocity. So after a time of about 5 tau, it has reached the terminal velocity. Let's look at the factor 1 minus e to the negative t over tau. When t equals 0, it is 0. As t increases, it gets closer and closer to 1. When t equals 0, the v is vt away from the final value of vt. When t equals tau, v is vt times 1 minus 1 over e, so it is vt over e away from the final value of vt. When t equals 2 tau, V is Vt times 1 minus 1 over e squared. It is now Vt over e squared away from the final value of Vt. When the time increases by tau, the velocity gets closer to Vt by a factor of 1 over e. Let's calculate the terminal velocity. At terminal velocity, the net force is 0. So here's the net force. Fg minus Fd equals 0, and we're using this free body diagram. So Fd equals Fg when it is at terminal velocity. Now let's model the grain of pollen as a sphere of radius r equals 10 micrometers and a mass of m equals 5 times 10 to the negative 12 kilograms. So this is how we can write the drag force for viscous drag. 6 pi eta r Vt. So eta is the viscosity of air. And mg is the force of gravity. Let's solve this for Vt. Vt equals mg over 6 pi eta r. Let's put in our numbers. Mass is 5 times 10 to the negative 12. G is 9.8. 6 pi, 1.8325 times 10 to the negative 5. That is the viscosity of air. And then the radius of the grain of pollen is 10 times 10 to the negative 6. And we get 0.014 meters per second. Note that this is much less than the value we measured for the coffee filter, which was 1.51 meters per second. The terminal velocity when we have viscous drag is much less than the terminal velocity when we have inertial drag. Let's look at the calculation of the time constant. For the same grain of pollen, radius is 10 micrometers, mass is 5 times 10 to the negative 12 kilograms, and the Vt which we just calculated, 0.014 meters per second. At terminal velocity, the drag force equals the force of gravity because the net force is 0. For viscous drag, we can write the drag force as V times V. In this case, it's V times Vt, since it is moving at terminal velocity. Force of gravity is mg. The time constant, tau, is m over b. So we can get that from this expression. Just divide by bg. Divide each side by bg. And then you're going to see things canceling out. B cancels out here on the left. G cancels out there on the right. And so we get m over b equals Vt over g. And so our tau becomes Vt over g. And let's put in our values. 0.014 over 9.8 equals 0.0014 seconds. The time to reach terminal velocity is about 5 times the time constant. So delta t is 5 times tau, which is 5 times 0.0014, which is 0.0070 seconds. Compared to the time for the coffee filter to reach terminal velocity from our experiment, it was 0.8 seconds. The time constant for viscous drag is the time to reach terminal velocity for viscous drag is much less than the time for inertial drag, as demonstrated here. Here's a graph of position versus time. I'm writing the position in terms of m squared g over b squared, and the time is written in terms of tau, the time constant. Here's what we get. It starts at 0, the position increases, the slope also increases, and eventually the slope becomes constant, and the function becomes linear after a time of about 5 tau. Let's compare with electric circuits. The differential equations, solutions, and time constants are similar for viscous drag, LR circuits, and RC circuits. Here's what we just found out for viscous drag. This is our differential equation, and we solve for v as a function of time. mg and b are constants, and the time constant is tau equals m over b. For LR circuits, this is what we have. This is our differential equation. The current is I. We want I as a function of time. And E, R, and L are constants. Notice the similarities between these two equations. So they will have similar solutions. And the time constant is just L over R. So we took the coefficient of the derivative. So for viscous drag, we took the coefficient of dv by dt and divided by negative of the coefficient of v, so m over b. And for here, coefficient of dv by dt divided by the negative of the coefficient of I, so L over R. And also, we have the RC circuits. This is our equation. Now we want to find Q, charge, as a function of time. And E, C, and R are all constants. What do you think the time constant will be for the RC circuit? Isabel? That is incorrect. Giselle? Yes, you are correct. It is RC. Isabel said that it is R over C, but it is R divided by 1 over C, which gives us RC. It's all right, because Isabel is taking this class for the first time, and we haven't yet gotten to LR and RC circuits. That comes in the next semester. Whereas Giselle has actually taken this course 6 times. She really loves this class. This is now a very exciting part of the presentation. That is why we have the curtains. We are going to look at a large object falling through air, a case of inertial drag. To continue, click on the next video in this series, Inertial Drag.